Okay, let's take some examples. Here we have a steel shaft in bending that has an ultimate tensile strength of 690 megapascal and a shoulder with a fillet radius of 3 millimeter connecting a 32 millimeter diameter with a 38 millimeter diameter. And that's the fillet radius of 3 millimeter, subjected to bending. And we're asked to calculate the fatigue strength concentration factor. So, to be able to use the chart to calculate the KT, you would have to calculate the capital D to small d, 38 divided by 32, and you would have to calculate R by the small d, which is the x-axis. Here, this is the capital D to small d, and this is the R to small d. Using these two values, and with this figure, you can get to the value of KT, which is 1.65. The equation for Kf is 1 plus Q into KT minus 1. So this is the KT value, 1.65. So remaining is the notch sensitivity, small q, from which you can get from this curve. So this curve will be provided to you, knowing the notch radius, which of course here is the fillet radius of 3 millimeter, and the ultimate tensile strength, which is around 0.7 gigapascal, you will be able to get the notch sensitivity q. All right. So you would substitute and get the Kf. And it turns out that the Kf is equal to 1.55. All right. So this value of Kf is the factor that needs to be multiplied with the nominal stresses acting in the fillet to account for the geometrical discontinuity. يعني لو عندي nominal stresses acting in the fillet 100 فلازم ال 100 دي تتضرب في 1.55 للأخذ في الاعتبار إن في geometrical discontinuity هنا، في عدم اتصال للشكل الهندسي هنا، في نزول مفاجئ من 32 ل 32 over this fillet. فالمكان اللي فيه الفيلت يعتبر geometrical discontinuity وهيؤدي إلى stress razors. It acts as a stress razor. It will concentrate the stresses at this point and magnify it by this value. Okay? Again, so this 1.55 represent the factor by how much this nominal stress needs to be multiplied للأخذ في الاعتبار إن هذه النقطة يصاحب وجودها هنا geometrical discontinuity. Okay? الطريقة الثانية هنا ما خدناها اللي هي Nober equation. So it will give the same value. So بس احنا ما خدناش. احنا will always be using this way of calculating the KF, the fatigue strength concentration factor. Okay. So this example is an extension for the previous one. امتداد للمسألة اللي قبلها. It is the same problem. It is determined that the fully corrected endurance limit is 280 megapascal. This is SE and not S-E. Fully corrected. Consider the shaft undergoes a fully reversing nominal stress in the fillet of 260 megapascal. So this is the value of the nominal stress that would be acting in the fillet. Estimate the number of cycles to failure. Okay. So this value of nominal stress acting in the fillet needs to be multiplied with the fatigue strength concentration factor that was calculated to be 1.55 to account for the geometrical discontinuity in the fillet. So the maximum stress in the fillet would be equal to the fatigue strength concentration factor multiplied by the nominal stresses acting in the fillet. So it's 1.55 multiplied by 260. So the maximum stresses that will be developed in the fillet due to the stress concentration is 403 megapascal. We're asked to calculate the number of cycles to failure. And here we will use the equation of SF is equal to A multiplied by N, which is the number of cycles to failure to the power B. The same equation that we have used in a previous lecture. Okay? The values of A and B are calculated through A and B are two constants that are calculated from these equations. If you can remember the equation, Fs ultimate كل تربيع over SE minus tult log Fs ultimate over SE. This is A and B. The SE is the fully corrected endurance limit. F is the fatigue strength fraction that can be defined from this chart. Chart دي أخدناها قبل كده. Knowing the ultimate tensile strength, you would go and get the F, which is the fatigue strength fraction. Okay? So, After calculating A and B, you would use the equation of SF is equal to A multiplied by N to the power B to get the N. The SF is the maximum reversed stresses acting in the fillet, which is 403 megapascal. So you will solve for N, which is the number of cycles to failure. So sigma reverse maximum, which is 403 over A, الكل أس 1 over B. So the number of cycles to failure would be 32.3 multiplied by 10 to the power 3 cycles. Okay. This is a new example. This is 1015 hot rolled steel bar. The word hot rolled here is an indicator, مؤشر لانه بيقول لي خد السيرفيس فينش فاكتور في اعتبارك. ال KA ليها value. Has been machined to a diameter of 25 millimeter. It is to be placed in reversed axial loading for 70,000 cycles to failure. Reversed axial loading معناها ان ال KB is equal to 1. The surface finish if the surface size factor, the size factor اللي هو ال KB is equal to 1 for axial loads. Okay. This is the number of cycles to failure, which is 70,000, and in an operating environment of 300 degrees Celsius. So this is the service operating temperature. You need to take the effective temperature. Now, using ASTM minimum properties and a reliability of 99%, so هنا بيقول لي take the KE into account, which is the reliability modification factor. Estimate the endurance limit and the fatigue strength at 77 cycles. Okay? I would prefer to use the word fatigue strength, of course, and not endurance limit, because it's a finite life of 70,000 cycles. Okay. So, to start, we would have to start with the effective temperature. Okay? You can either فاكرين تأثير التمبريتشر بناخده بطريقتين. The route number 1 will be followed if the information available to you is the ultimate tensile strength at room temperature. So if I'm giving you in the ultimate tensile strength of this material at room temperature is 340 megapascal, so you would have to go with route 1. هتروح على التيبل الخاص بالتمبريتشر افكت ومن خلال هذا التيبل هتحصل على هذه الريشيو, which is the ratio of the ultimate tensile strength and the service operating temperature, which is 300, divided by the ultimate tensile strength at room temperature. So هتروح عند 300 درجة وتشوف الريشيو دي طلع كام. هتلاقيها 0.975. ومن هنا هتقدر تحسب الالتيميت تنسايل سترينث للماتيريال دي عند ال 300 درجه. هتضرب ال 0.975 اهي في الالتيميت تنسايل سترينث at room temperature اللي هي دي, هتحصل على الالتيميت تنسايل سترينث at the temperature of 300 degrees Celsius. Okay. Now you can calculate the endurance limit. This is the corrected ultimate tensile strength خلاص. So you can calculate the endurance strength or endurance limit. أنا عارف إن في الستيلز في علاقة بين الendurance limit والultimate tensile strength. SE is equal to 0.5 S ultimate, provided that this S ultimate تكون أقل من 1400 ميجا باسكال زي ما خدنا في أول محاضرة. So this value is less than 1400 of course. فالendurance limit is 0.5 في هذه الفاليو. So this is the S-E that needs to be corrected for other parameters like surface finish, size, loading, and others as well. Okay, like KA, KB, KC, and so on. Let's start with the surface finish factor. The table for the surface finish factor will be provided to you, of course. هيكون معاك. هتروح على الهوت رولد هتشوف ال A will be ال KA هي عبارة عن A S ultimate أس B. The S ultimate is the corrected value of the ultimate tensile strength at 300 degrees Celsius اللي أنا حسبتها هنا. Okay. وال A وال B دول يا جماعة are totally different than the AB constants used in the equation of SF is equal to A في N أس B. أنا عندي equation خدتها من المحاضرة اللي فاتت إن الفاتيك strength SF is equal to constant equal A اسمه A في number of cycles to failure اللي هي capital N to the power B. Okay, so these two AB here that are used to calculate the surface finish modification factor are totally different عن ال A وال B اللي موجودين في معادلة ال SF. Okay. Anyway, so here I will calculate the KA. For axial loading, I know that there is no size effect. KB is equal to 1. A loading modification factor will have to take a value لأن عارف إن اللود إن ال S-E is always based on bending. So if the fluctuating loads is changed to another mode than bending, then the KC will have to take a value. هروح للتيبل أيضا بتاع الأكسيال لود وهشوف إن ال KC is equal to 0.85. أنا already أخدت ال effective temperature بالطريقة الأولى. I will have to substitute for KD to be 1. قايل لي إن reliability is 99%. So I will go to the table for the reliability modifying factor and I will get KE value. He did not mention anything about the miscellaneous effect factor. So I will have to take KF to be 1. Okay? So now I will correct for the endurance limit. This is the fully corrected endurance limit, which is equal to KA size factor, surface finish factor, size factor, loading modification factor, temperature factor, reliability factor, miscellaneous effect factor, and this is the S-E that was calculated in the previous slide. زي ما انتم شايفين ال KD was substituted for 1 now لأن already I've taken the effective temperature. خلاص. طيب. Now I've reached the fully corrected endurance limit. Okay? And I want to calculate the fatigue strength that corresponds to a number of cycles to failure of 70,000. So I will use the equation. SF is equal to A n to the power B, where A and B are two constants. أهو. F as ultimate كل تربيع over SE وminus تلت log F as ultimate over SA. Of course, this is the fully corrected endurance limit. And this is the fatigue strength fraction. So that chart for the fatigue strength fraction also will be provided to you. عن طريق ال ultimate tensile strength هتروح تجيب قيمة ال F. هتعوض عن A وال B ثم هتقول إن ال SF بتساوي A n to the power B هتعوض وهتجيب ال fatigue strength. Let's see another example. Here we have a shaft, stepped shaft, 32 millimeter, 38 millimeter, 35 millimeter, supported. This is the reaction at the two supports with an external load of 6.8 kilonewton that causes bending on this shaft. This shaft could be مثلا shaft في gearbox stepped ويكون مصدر اللود ده جاي من إن في هنا ترس engaged with another gear. Due to the engagement بيبقى عندي force. عندما تنتقل هذه الفورس إلى الشافت بتبقى عمودية على المحور الطولي لهذا الشافت فبتسبب فيه bending. ده البندنج مومنت دايجرام الناتج من هذا البندنج لود. Okay, this shaft is being subjected to a completely reverse cycle of load. النقطة دي من الشافت معرضة لكمبريشن والنقطة المناظرة ليها تحت معرضة لتنشن. لما الشافت ده بيلف النقطة اللي كانت subjected لكمبريسيف بتروح تتعرض لتنشن واللي كانت معرضة لتنشن بتروح تتعرض لكمبريسيف. So each point in the material is being subjected to plus sigma and minus sigma, which means a completely reversed cycle with a mean stress of 0. Okay? الماتيريال المصنع منها هذا الشافت is IZ1050 and it's called drone steel. This to give information about Ka, which is the surface finish factor, and all the fillet radiuses on the shaft is 3 millimeter. Okay? So the information about the available information about this material is S ultimate. The ultimate tensile strength is 690 megapascal and the yield strength is 580 megapascal. طيب اول حاجه هنعملها ان احنا هنحسب الendurance limit is 0.5 S ultimate. This is the endurance limit based on the estimate, and now we need to modify it using modification factor. Knowing that it is cold drawn هروح على التيبل بتاع surface finish modifying factors وهطلع constants A and B. So Ka بتساوي A as ultimate أس B. This is the surface finish modifying factors. Okay. Now the size factor. This is 32. Okay. So أنا عارف في السيرفيس في السايز modifying factors في معادلتين based on the value of D. I will check that 32 lies within which range, and I will use the appropriate equation to calculate KB. This is the size factor. بعد كده ال KC اللي هو load modifying factor is equal to 1 because the problem here is all about bending. وبالتالي مش محتاج ان انا اعمل modifying للvalue of S-E. KD is the temperature factor, and since nothing is mentioned about temperature, I'll assume KD to be 1. This is the reliability factor, and again, it's not mentioned, so I'll use it as 1. And there is no mention for the miscellaneous effect factor, so I'll put it as 1. Okay? And now we need to correct for the endurance limit. I have only KA and KB. So KA multiplied by KB multiplied by the estimated endurance limit. Here I'll get the fully corrected endurance limit, which is 236 megapascal. Now you need to analyze this problem to check where is the most critical point from which you should start the design process. أنا عارف إن النقطة دي corresponds to the maximum bending moment. Okay? But this point does not have any geometrical discontinuity. So the stress calculated at this point will not be multiplied by a magnifying factor. But let's compare this to point B, for example. Here I have a geometrical discontinuity that will magnify the value of stress at this point. Okay? I have stepping up from 32 millimeter to 38 millimeter. Okay? I have also another point C, which again, I have a stepping up from 35 to 38. So which point is more critical? Of course, I will disregard, يعني هستبعد النقطة اللي ما فيهاش geometrical discontinuity, because at this point the stress will be just calculated as MC over I and will not be multiplied with a stress concentration factor اللي هو fatigue strength concentration factor. طيب, let's compare point B and point C. Which of them is more critical? Point B لو بصيت على bending moment diagram هتلاقي ان moment at point B is relatively higher than the moment at point C. Okay? Besides, the diameter بتاع الشافت اللي عند point B is the lowest diameter, which is 32 here, compared to 35. So, of course, point B by analysis will be dealt as هبص عليها كأنها is the most critical point from which I need to start my design process. Okay? فهبتدي أحسب fatigue strength concentration factor at point B. Here it's like a fillet. I have stepping up from 32 to 38 with a fillet radius of 3 millimeter. This information, of course, will be given to you. I will calculate the fatigue strength concentration factor, which is equal to 1 plus Q into KT minus 1. I will use the appropriate chart to calculate KT. Okay, it will come out. Remember, capital D to small d and R to small d. From the chart, you will be able to get the value of KT, which is 1.65. بعد كده هروح على الشارت الخاصة بالنotch sensitivity Q وهحسب ال KF. Okay? هنا ال KF is calculated using the Nober equation, which we cancelled earlier. احنا لغينا ال Nober equation. So I will not use this way to calculate KF, but I will use the relation that we have come to know before. In the KF, it's say 1 plus Q into KT minus 1. And if you calculate it this way, you will end up with exactly the same value of KF calculated هنا من خلال the Nober equation. So it's 1.55. So the next step is to calculate the bending moment at point B, and then to calculate the nominal stress at point B, which is due to bending, MC over I, and then multiplied with the magnifying factor, lower fatigue strength concentration factor. Again, this is the equation, this is the shaft with the two supports and the bending load and the bending moment diagram. As we said, the first thing to do is to calculate the bending moment at point B, either by method of section or by multiplying the support with the arm distance. So you finally get the value of the moment at point B. And then you would go and calculate the stress at point B, which is MC over I. This is the moment at B multiplied by C divided by I. When you calculate the stress at point B, you will have to multiply it by the fatigue stress concentration factor, which was calculated as 1.55. Okay? So this is the maximum stresses acting at point B due to the existence of geometrical discontinuity. نتيجة ان انا عند point B في geometrical discontinuity which is the fillet, the stress, the nominal stress calculated will be magnified by 1.55 to reach this maximum value of stress acting at point B. And this is the stress that you need to use for any design purposes at point B. طيب. Now I know that the S ultimate for this material هي 690 megapascal. I know that the fillet radius is 3 millimeter. Okay, so I can go and calculate now the constants A and B. وهستعمل الإيكويشن SF اللي هو fatigue strength بتساوي A في capital N اللي هو number of cycles to failure to the power B. And these are the two constants A and B. FS ultimate كل تربيع على SE والB بتساوي minus 2 log FS ultimate over SE. Okay. طبعا ال SE هي ال fully corrected endurance limit. F هو ال fatigue strength fraction اللي بجيبه من الشارت اعتمادا على ال S ultimate. So for this value of S ultimate, I will use the chart to get the value of F, which is the fatigue strength fraction, which turns out to be 0.844. So I will calculate A and you will calculate B. بعد كده you will use the equation. SF is equal to A multiplied by N to the power B, but here you will solve for N, knowing that SF هو ال fatigue strength هو ال maximum stress acting at point B. So I will solve for N here. It's SF, which is sigma A, which is the reversed amplitude stress acting at point B, the maximum value of course, على A الكل أس 1 over B. So for sigma A, I will substitute the sigma max that was calculated here by multiplying the nominal stress, MC over I, by the fatigue strength concentration factor, which is 1.55, to account for the geometrical discontinuity existing at point B. الأخذ في الاعتبار أن عند نقطة B عندي geometrical discontinuity, عدم اتصال الشكل الهندسي. This is the stress that should be used in this equation. على ال A اللي هو ال constant اللي جبته من هنا الكل أس 1 over B. So it's 1 over this B value. The number of cycles to failure will be 68,010 أس 3 cycles. Okay, for this problem.